Welcome to AI Explains. Today, we're doing a deep dive into what is, maybe, the single most important paper of the last decade in AI. It's the 2017 Google Brain paper, Attention is All You Need.
It's funny you say that because it's so true. It's really rare that you can point to a single document and say, this is where the world changed.
And if you're using ChatGPT or Claude or really any modern AI, you are using the architecture that was laid out right here.
Exactly. So most people have heard of the transformer model that came from this.
Right, but I want to get into the why. Why did this specific architecture win so decisively? To do that, I think we have to look at what it replaced.
Okay, so before 2017, the whole world of language processing was dominated by something called recurrent neural networks, or RNNs.
Specifically LSTMs, right? Long short-term memory networks.
That's the one. And their defining feature, or maybe their defining problem, was that they were sequential.
Sequential, meaning they had to process words in a strict 1, 2, 3 order.
Exactly. So if you give it a sentence, say, the quick brown fox, it processes does some math, then carries that result over to process quick, and so on. It's a chain.
Which, I mean, that sounds logical. Language is a sequence.
It is logical, but it's incredibly slow. It creates this massive bottleneck because you can't start working on the end of a sentence until you've finished the beginning.
So you can't parallelize it. You can't just throw more computer power at it to speed it up.
You get it. And what's worse, for long texts, the model would often, forget what the first few words were by the time it got to the end.
The context just faded away. So then comes this paper. Attention is all you need. What was so radical about it?
Well, the title says it all. Their idea was to just throw out the recurrence entirely. No more word one than word two. They built a system that could look at the entire sentence all at once.
Okay, that sounds like chaos. If you look at everything at once, how do you know how the words relate to each other?
That's the magic. That's the attention mechanism.
Yeah.
Think of it like this. Normally you read left to right. Now imagine you could look at a whole page of a book instantly, and your brain just automatically highlights all the connections. It shows you how this word over here is related to that word way down there.
So it's weighing the importance of every word to every other word all at the same time.
Precisely. It learns to pay attention to the most relevant parts. In a sentence like, the animal didn't cross the street because it was too tired, attention helps the model know that it refers to animal, not street.
That sounds incredibly complex, though. A lot of connections to track.
It is. And that's why they didn't just use one attention mechanism. They introduced what they called multi-head attention.
Multi-head?
Yeah, in the paper, they used 8 of them, all running in parallel.
And what's the point of that? Is it just for, backup?
No, it's for perspective. Think of it like looking at something with 8 different pairs of glasses. One head might be focused on grammatical structure. Another might be looking at, say, conceptual relationships like king and queen.
So by combining all those views, you get a much richer understanding.
A much richer, much more nuanced picture, yes.
Okay, but I see a problem. If you throw all the words into a bag at once, you've lost the order. The dog bit the man is totally different from the man bit the dog.
That was the single biggest challenge they had to solve. If you remove the sequence, how do you get it back? And their solution was, well, it was brilliant. They used positional encodings.
So they tag each word with its position.
In a sense, they used sine and cosine waves to give each position in the sentence a unique mathematical fingerprint. It's a way of stamping the location onto the word's data without having to process it in order.
So the model just knows dog is in position 2 and man is in position 5.
Without ever needing to read them sequentially. It gets the order and the context all at once.
Let's talk results. How well did it actually work?
It didn't just work, it crushed the previous records. On English to German translation, they set a new state-of-the-art score. Same for English to French.
But at what cost? Usually, better performance means way more expensive training.
And that's the kicker. It was actually cheaper, dramatically so. Because it was all parallel, they could use modern GPUs to their full potential.
How much cheaper?
They trained their big model in just 3.5 days on 8 GPUs.
3.5 days? And the competition
was taking weeks for similar tasks. This wasn't just an improvement. It changed the economics of AI research. Suddenly, you could experiment and iterate so much faster.
Which explains the explosion we've seen since 2017.
Absolutely. They unlocked a new way to scale. And they even hinted at it in the paper's conclusion that this could go way beyond text to things like images, audio, video.
And today, we see that everywhere. It really makes you think. If this attention idea lets a model see the whole picture instantly, processing all these connections at once.
Yeah.
Are we heading towards a future where AI has a kind of photographic memory for any complex data, and that old, slow, step-by-step processing just becomes obsolete?
It's a fascinating thought. And it certainly feels like that's the direction we're moving in.